In this video, we're going to look at Hess's Law. And what Hess's Law says is that a chemical reaction can be written as the sum of two or more steps. And when you take these steps and you add together their individual enthalpies, you get the delta H for the reaction that you're interested in. So if you remember back to the last video, we learned how we can manipulate these thermochemical reactions. We can either multiply them by a factor or we can flip them around. And the reason why we learned about that was because now when we do Hess's Law, we can take some stepwise reactions and we can manipulate them to get them to add up to give us a chemical reaction that we're interested in. So let's just look at a quick example. So like, for example, if we were to take 2H2 gas plus O2 gas, and this gives 2H2O liquid. So you'll notice this is very similar to one of the reactions we wrote in the last video, except in this case, instead of the product being a gas, the product is a liquid. We don't know the delta H for this. This is something that we haven't done experimentally. We can't set up a calorimeter to do it because we don't necessarily know that all of our water product will condense to be a liquid. So in this case, we want to figure out what would the delta H be for this reaction if we know some things about other reactions that are pertinent. So for example, we know the following. So we know that 2H2 gas plus O2 gas goes to 2H2O gas, and we saw the delta H for this was equal to minus 483.6 kilojoules. And then now if we want to work with this as liquid as being a product, well, we can look at the reaction of the physical process where H2O gas goes to H2O liquid. This is called condensation. And we can figure out what this process has for delta H, and we can look that up. And the delta H for this particular process is minus 43.9 kilojoules. So now what we want to do is, we want to know is, can we add these two up to give us our correct reaction that we have above and then get the delta H? Well, we can do that. The first one looks good. That has all of our products and our reactants. And then the second one also looks good because it's taking us from the H2O gas to the H2O liquid. The only problem is we have this 2 coefficient up here, but we don't have a 2 coefficient down here. So what we have to do is we have to multiply this one by 2 in order to get that to cancel out. So when we multiply this by 2, what's going to happen is we're going to get 2H2. And the way that I like to denote this is, instead of putting it in parentheses, over here on the right, I'm just going to do a multiply by 2 so that I know what I did. So that's going to give me a 2H2O gas, a 2H2O liquid, and when we know that when we multiply by 2, we have to multiply our delta H by 2 as well. So this is going to give us minus 87.8 kilojoules. As the new delta H. So now we have 2H2O gas goes to 2H2O liquid. And when we add all this up, the 2H2 is going to come down. The O2 gas is going to come down. The H2O gas is going to cancel out with the other H2O gas, since it's a reactant on this side and a product on that side. And we're going to be left with 2H2O liquid. So this is the reaction that we're interested in. And so, like Hess's Law says, we're now going to add up the two delta H's. So we're going to take minus 483.6 plus negative 87.8, and we're going to get minus 571.4 kilojoules. So what we did was we basically took 2 steps. So these are the stepwise reactions. We got them so that when we added them up, it gives us the reaction that we're interested in. Then when we combine the delta H's, we get the delta H for the reaction that we're not sure about. So this is what we would call a non-experimental way of determining delta H. And this is typically done when you can't do something in a calorimeter, or it's done when you can do some steps of a reaction in a calorimeter, and then you combine those steps to get the theoretical delta H. So that's why we do Hess's Law. Now let's take a look at how we can define some steps for how to approach these. In this slide, we have some steps that will allow us to go about doing Hess's Law in a systematic way. So the first step says arrange each step so that the products match the products and the reactants match the reactants. So what we want to do is we want to take a look at each one of these steps, and we want to make sure that the products are on the product side and the reactants are on the reactant side. If a step has neither a product or a reactant in the final reaction, arrange the step so that it matches the reactant or product of another reaction arranged in step 1. So this is not always necessary, this step, but basically you may get a reaction, like let's say that you get 3 or 4 reactions, and one reaction has nothing that's in the reaction that you're interested in. It's all basically what we call intermediates. These are compounds that are produced in a stepwise fashion that get produced in one stepwise reaction and then consumed in another. So they don't appear in the final reaction, but they do appear in the mechanism, is what we call that. So what you would do is you would look to see, based on the other reactions, how you could orient that in terms of reactants and products so that they'll cancel out. The intermediates will cancel out. And then, of course, we have to multiply coefficients so that the coefficients match that of the final reaction. So let's start applying these steps here. So for the first one, we have 2 aluminum plus 3/2 O2 goes to aluminum oxide. Now let's take a look at the reaction here. So I have 4 aluminum, but only 2 aluminum here. So my aluminum is correctly oriented. That is a reactant. So I'm probably going to leave this one the same. And look, Al2O3 is a product in the reaction that we're interested in. So we're going to leave this one the same, but we have to get it so that the coefficients match. And I can see already that because I have a 4 and a 2, I'm going to have to multiply this one by 2. So I kind of put that over on the side, what I did, and then below I'm going to write my reaction so that it's multiplied by 2 with the new delta H. So we get 4 aluminum solid plus 2 times 3/2 is going to be 3 O2 gas, gives 2 Al2O3 solid. Okay, and then I can cross this one out because we've just taken care of that. Now we have to take care of the delta H. So the delta H now is going to be 2 times that delta H, so we get minus 3352 kilojoules. And I'm just going to cross this out. Now if you were doing this on a piece of paper, because I'm just doing this on the slides, I'm doing it below. If you're doing it on a piece of paper, you are perfectly welcome to rewrite the reactions down below. You don't have to do this crossing out thing if you don't want to. You can start fresh in the blank area of a piece of paper, just like you can imagine me writing this on the board. I'm just doing it this way because of the limitations of the presentation method that we're using. Now let's look at the manganese reaction. So in this case, we have Mn solid plus O2 gas goes to MnO2. Now I notice that MnO2 and Mn are not on the correct side. I have the MnO2 as a product in my stepwise reaction, and I have Mn as a reactant, but that's supposed to be flipped. So I know that I'm going to have to at least multiply this by a -1, for sure. But also I noticed for this one that there is supposed to be 3 MnO2 and 3 Mn as my coefficients. So I'm not going to multiply this one by -1, I'm going to multiply this one by -3. Because I have to get the coefficients right. So if we do that, we're going to get 3 MnO2 solid goes to 3 Mn solid plus 3 O2 gas. Now I can cross this out because I've taken care of it. And then I have to multiply my delta H by -3. So if I do that, I get delta H now is equal to plus 1563 kilojoules. So now we can add everything up. So let's make sure that our reaction works out. So I bring the 4 aluminum down, solid. I bring the 3 MnO2 down, because that doesn't cancel out with anything, solid. And I notice here that I have 3 O2 on the left and I have 3 O2 on the right. Those are going to cancel out since they're on the reactants and product side. And then this is going to give me 2 Al2O3 solid plus 3 Mn solid. And so this checks. That is the same thing as my reaction. So then I'm going to get my delta H, which in this case is going to be, I add up -3352, and then I add to that a positive 1563, so I get a -1789 kilojoules. And that checks out. So that's how you do it for a simple one. Let's take a look at an example of a little bit more challenging one. So on this slide we have some practice examples of slightly more challenging ones. So let's look at these in turn. So for the first one, it says 2 carbon plus 4 H2 plus oxygen gives 2 methanols. So in the first one, I notice already for this one that I'm going to probably have to do some kind of flip here, because I have a methanol on the right side, but I have on the product side in my target reaction, but the methanol is on the reactant side. So I know I'm definitely going to have to do a -1 for this one. But let me check the coefficient. So I have 2 methanol in my product, so I know that I'm going to have to do a times -2 here. So if I do that and I flip everything around, I'm going to get 2 CO2 plus 4 H2O gives 2 CH3OH plus 2 times 3 halves is 3 O2. And I'm going to do the same thing for my delta H. So when I do that and I multiply by -2, I'm going to get plus 1453.6 kilojoules for my new delta H. And so now I can cross out the first one because I know I've taken care of it. Now let's look at the second one. So the second one says carbon plus oxygen gives carbon dioxide. This one's looking good because I have my carbon as a reactant in my target. I have my oxygen as a reactant in my target. So I think I'm okay here. I'm not going to flip it, but I do need to get the coefficients right. So in this case, the carbon has a 2 in front of it, so I have to multiply this by 2 to get that carbon to be a 2. So this one's definitely going to be a multiply by 2. Now, let me give you a little bit of a tip here. You might be tempted to get a little nervous because of the oxygen. You might be saying, well, if I multiply the oxygen by 2, I'm not going to have a coefficient of the oxygen by 1 up here, which is what we need. However, if you notice, we have some oxygen in the first one. So this oxygen is going to be something that's probably going to wind up canceling out and working out at the end. So I'm focusing on the ones that don't only appear on one side. So the carbon solid, that only appears on one side and is not in any other reaction. So that's why I'm multiplying this one by times 2. Because I know for sure that in the end I have to get my carbon to be a 2. And in none of these other stepwise reactions there's a carbon. So when I do that, I get 2 carbon solid plus 2 O2 gas goes to 2 CO2 gas. And so my delta H here is going to be 2 times that answer, which is going to be -787, sorry, I just had to check my notes, 0.4 kilojoules. Okay, now let's look at the last one. So we have H2 plus 1/2 O2 goes to H2O. So in this case, I have 4 H2 up here. H2 doesn't appear in any other one, so I know I'm probably going to have to multiply this one by 4, but let me just check. So checking that along, all of the other ones appear in other ones. This H2O appears up in the first one, the O2 appears up in the first one. So I'm just going to multiply this one by 4 to get my hydrogen to work, my hydrogen gas. So this is going to give me 4 H2 gas plus 2 O2 gas, because 1/2 of 4 is 2, gives 4 H2O liquid. And now my delta H for this one is going to equal -1143.2 kilojoules. And you can obviously cross these out. I just forgot to do that. So now let's check to make sure that everything cancels and we get everything right. So our carbon dioxide is going to cancel. That's going to go away. Our waters are going to go away because we've got some waters on the left and we've got some waters on the right. Now we got to figure out our oxygens. So we have 3 oxygens on the right and we have 4 oxygens on the left. So this is going to give me a net of 1 oxygen on the left. So I'm going to cancel out one of those, and this is going to go to a 1 because I have 3 on the right. So if I bring everything down, I have 2 carbon solid plus O2 plus 4 H2 gas goes to 2 CH3OH liquid, which is what I have up top, and we are good. This checks out with what I have above. So now we just have to add up the delta H's. So we add 1453.6, we add a -787.4, and then we subtract again 1143.2. So we get an overall delta H of -447 kilojoules for that when you combine those together. Okay, let's take a look at the last one. So in this case, we have NO plus O3 goes to NO2 plus O2. So the NO is in the right spot, and the NO2 is in the right spot, so we're not going to do anything with this one. This one looks like it's good because there's a 1 here for the NO, there's a 1 here, there's a 1 here for the NO2, there's a 1 there, so I think we're okay. I don't think we have to do anything with this one. Now let's look at this middle one. O3 goes to 3/2 O2. So in this one, this is interesting because remember what I was talking about in the second step where it says if you don't see anything that's in the reference reaction, you have to check to see what's going on with the other reactions? Well, this is that case. These are what we would consider to be all intermediates. The O3 and the O2 do not appear in the above reaction. So what we're going to do is we're going to try to fix this one so that it's going to cancel with the other ones. So if you notice, we have O3 gas up here and we have O2 gas up here, and it's opposite of the way that we have it in this reaction. So we're going to have to definitely flip this reaction to get that to work out, right? Because we have to get O3 to cancel with the O3 and the O2 to cancel with the O2. So I'm going to multiply this one by -1, and that's going to give me 3/2 O2 goes to O3 gas. And we're just going to, so we can cross that out, and we can cross this out and make delta H equal to a positive 142.3 kilojoules. Now let's take a look at the last one. So this one looks like we're going to have to do something to it. The O2, the 2O in this case is on the wrong side. So with this one, I definitely am going to have to flip it. But also, I'm going to have to, it looks like I'm going to have to take this one by 1/2. Because if you look, there's a 2 here, but there's only a 1 here. So this one I'm going to do a -1/2 to this one. So when I do that, that's going to give me O gas goes to 1/2 O2 gas. And when I fix my delta H, this is going to give me minus... Hang on, let me just check something. Oh, yeah. This is going to give me minus 247.5 kilojoules. I just had to check my sign there. Okay, so now it looks like we have everything right. We have all of our stuff correct. So let's start canceling things out. So our 1/2 O2 is definitely going to go away. And we're going to have, if we subtract 3/2 O2 minus 1/2 O2, that's going to give us 1 O2. And then up here we have an O2, which is going to make that go away. So that all goes away. So if you take 3/2 O2 minus 1/2 O2 minus 1, that's going to give you 0 O2. So it all goes away. Our O3 is going to go away. So we're left with NO gas plus O gas goes to NO2 gas. Now, if we add up our delta H's for this one, we're going to get minus 198.9, add to that a positive 142.3, and then we're going to add to that a negative 247.5. That's going to give us minus 304.1 kilojoules. So that shows you Hess's Law and how to deal with working with Hess's Law. It takes some practice, but in the end, it's a very straightforward process, and you just have to make sure you do all your accounting correctly and follow the steps.